Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is on the analysis of fastener patterns when they have an eccentric loading. This is a very important concept. Let's see how it works. So we've gone through basic standard non-aerospace fasteners and what I call aerospace fasteners, including rivets, lock bolts. Some people keep getting bent around the axle about a bolt versus a lock bolt. They have different interaction equations. It looks like most of you figured that out though. So today we're going to start looking at how to analyze fasteners. Now, if you think back to Aero 3261, lecture 4, I believe it is, where we covered the various checks we make when we have fasteners involved in a joint. We looked at net tension, shear, bearing, and tear out. We then looked at, in the last couple lectures, we included a little lecture on bolt bending, which we had ignored before. Today we're going to do is look closer all those fastener analyses where we're looking at lap shear or double shear fasteners were of the simplest of fasteners. So if you're still throwing away those points, you're going to want to study those joints so you understand how to calculate the appropriate loads. However, we're going to find out that those are the simplest, and whenever we have what we call an eccentric fastener pattern, where the load does not pass through the centroid, it's actually a little more complicated. So let's take a look what I have for you here. This is just some typical examples of what real structures look like in aerospace, aircraft specifically, and what some of those fastener patterns might look like. So let's go back and let's focus on a single lap joint with a single fastener loaded as shown. If we have that, we see we have a force P, and the force per fastener is simply P. We call it S. I like to use S for shear of those forces, but we can see that if we just sum forces along the line of action, that our force in the fastener is simply P. That's going to be the force used for net tension. That's going to be the force used for bearing. That's going to be the force used for shear tear out. If we check that, that's going to be the shear force in the bolt. The key point here is that the line of action of that fastener pattern passed directly through the centroid of the fastener pattern. And in this case, the fastener pattern only had a single bolt, so right through the center of the fastener. Got that? Okay. Now let's take a look at a joint where we have two fasteners. We again have a central force loaded right through the centroid of the fastener patterns, and we can see, as we saw back in 3261, that our force per fastener is now just P over 2. That's the force that we would use for net tension, for bearing, tear out, shear. Okay? But the key point here is that force passed right through the centroid of the fastener pattern such that all we had to do was just take P over the total A. The total A, if you imagine taking a hacksaw and cutting those two pieces apart, well, we're going to end up with just the two diameters of the bolt, the area of which is pi d over 2 squared times two fasteners. Since the line of action went right through the centroid of that, then our stress is just P over A. Now let's take a look at a joint. Let's say this plate is mounted to some other structure with two bolts. And let's say we have a moment applied. Now, it's going to be a little more challenging. We cannot use what we've already learned to solve this without going back to statics and equivalent load systems. Here's how it works. And once again, we're focused on, imagine taking, if you've ever grabbed a hacksaw blade without the hacksaw and tried sawing through something, we got these two things that are fastened together with a fastener, And now we've got a hacksaw blade that we're separating them, and we're looking at what shanks of the fasteners we just cut through, okay? So we've got this little loading on the thing, and this is equal to the reactions in the fasteners will be like this. Now, if we don't know what the directions are, that's not critical. We can just draw both reactions upward. They're both shear forces, so we can call them S. And then we can sum our moments to determine what they are. So let's do that. Now, once again, this is a action-reaction pair. We have a moment applied, and what I have drawn here are the reactive forces in the fasteners. So if we sum our moments about point 1, the center of the fastener 1, we see we have the positive, and we're going to call this right-hand rule positive. We have the moment minus A times that S2 equals 0, which means S2 is simply M over A. That's just a couple, right? This is going to be reacted as a couple between these fasteners, going back to statics. If we sum our forces by now in the 0 in the vertical direction, then we have S1 minus S2 for the way it's drawn equals 0, and we find out that S1 equals S2. So now we find that both forces are just M over A. And if you were really good at statics, you could have spotted that by inspection, because we say, wait a minute, we have a moment, and it's going to be reacted as a couple. Since there's no external forces applied, the sum of forces has to be 0, which means this moment is going to turn into just a simple couple on these fasteners, which means two equal and opposite forces separated by some distance, M over A equals S. Got it? Okay.
Yes.
Lex, you are the man. I'm going to give you a point for being with me. Okay, with that said, let's go to a slightly more complicated case. Oh, we already said this. Once again, these are reactions that we've shown here. Okay, let's look at another case. We've got the same joint, a plate mounted to something else with two bolts. We have an eccentric force. Now what happens? Well, we're going to have to be a little more careful. This force does not load the fasteners through the centroid of the pattern, which means it's going to create an eccentric load. So we're going to resketch this. And first, what we need to do, going back to statics first couple lectures, is come up with an equivalent force system at the centroid of the fastener pattern. Now, sometimes, actually shortly, we're going to learn how to calculate the centroid of fastener pattern. But right now, we can spot by inspection if these bolts have the same diameter, the centroid of that pattern, if we define X and Y like this, then the center of the pattern is just A over 2, 0, right? Okay. With that said, we can see that our force, this PO at the centroid, is just P, and the moment is just P times the eccentricity of the load, this perpendicular distance, which in this case is going to be A over 2 plus B, because it's this distance right here. This is that eccentricity of the load from the centroid of the fastener pattern, and that happens to be A over 2 plus B. Do you see that? Okay. Now, if we draw the, these are the equivalent forces. Looks like there's an E missing from equivalent. We're going to see, now take a look at the two things. First, we can look at PO. The equivalent, PO is going to be reacted equally between these fasteners because it's now at the centroid. So it's called, PO is equivalent to these P over 2 forces, or it's reacted by P over 2 forces like this, okay? Equivalent, reactive. That moment is going to be equivalent to a couple, that's the purple ones, it's equivalent to this couple, PM, where PM is just M over A. The reaction is going to be like this. The equivalent force system is like this. So you can see here, we have two forces. We have this PO is distributed P over 2 to each fastener, and the PM, the force due to the moment, is just a couple. When you add these two together, you get the total force on each fastener. So S1 is going to carry P over 2 minus PM, and S2 is going to take P over 2 plus PM. You guys got that idea? Okay, this is setting the groundwork for our understanding of what we're going to do today. So let's keep this in mind. We're going to step back a step and we're going to walk back through how this works. All right, so let's backing up here. Let's take a look at this lap joint. We can kind of see how the load transfers. If we have 2,000 pounds per inch, it's going to run down the first plate. It's going to run down the first plate. It's going to start transferring up here. Some of it will continue and transfer here. Some of it will continue and transfer here, such that that 2,000 pounds per inch is going to transfer 1/3 of it through the first fastener, 1/3 of it through the second fastener, 1/3 of it through the third fastener. Then we have all of the load, which then comes out 1/3, 1/3, 1/3, and it's all back into the plate. That's how the load goes through. Now, it's actually when folks in industry, that's usually how we start to analyze it. And often that's all we'll do for static. But when we start looking at fatigue and damage tolerance, we generally note that the load distribution between these is actually not uniform. Often the first and the last fastener end up picking up more load than the others. And there's a lot of analysis that's done around trying to figure out what the correct force distribution is. But for our purposes and for most of the work in industry, we're just going to pretend that that carries a load equally. And that's mostly true when we deal with static ultimate kinds of loads. Okay. All right. I think I have a couple questions for you here on this slide. So, do these fasteners experience single shear or double shear?
Single.
Okay, I got one single. Anybody else? Okay.
Double.
Double. Great. I got one ace, one pass, and everybody else fails. Sometimes you just stick your stuff on the wall, good or bad. These are actually single shear. It looks a bit like a double shear joint. If we had another plate down here, that would be a double shear joint. But there's not a plate down there, so each of these only has a single. When you look and separate these at the shear plane, you'll notice you only have one shear plane. That's a single shear joint. Does that make sense?
Yeah.
Force per fastener, what's that? P over 3
P over A.
case. And then we need to check all of our stuff. We're going to need net tension. We're going to need shear. We're going to need bearing, maybe tear out. And we might want to evaluate bolt bending. Okay. All right. Okay. So now we're ready to go back to looking at what are the, now that we've kind of refreshed our memory about basic bolts and we kind of preset the groundwork for how we're going to analyze these puppies, we're now ready to go back and look at a simple joint. Now, if you look at this, we can see this force is passing. We can actually see if all these fasteners have the same diameter, then actually this load passes through the centroid of the pattern, which means it's going to be equally distributed between the fasteners. Just like force, P is distributed equally P over A, and then we add or subtract the MC over I component. In the same way, we're dealing with fastener patterns, an axial load through the centroid will distribute evenly between the fasteners. So here's how it works. We got this bolted joint. Let's say we have this force here. We can see that. We can see that also is going to be, since that's passing through the centroid, we're going to get equal force, 1/4 of that on each fastener. All right. Now let's take a look at this guy. Now we can see that this load is no longer applied through the centroid of the fastener pattern. So it's going to be a little more complicated to evaluate the fastener pattern. What we're going to have to do is come up with an equivalent force system at the centroid of the bolt pattern. Now, in this case, we can spot where the bolt pattern is. It looks like it's, if we actually, and what I like to do whenever I'm analyzing fastener patterns, I'll take the lower left fastener. I'll call that the origin. I'll define the X like this and the Y like this. I'm going to highly recommend you all do the same thing. You will actually find that's the easiest way to do it. Then we can identify what the location of each center of each bolt is, and we can construct our table for analysis. This will be most easy to implement. We then will figure out where our centroid is, our X bar, and we'll find out where our Y bar. That's where we're headed. Right now, though, we can look, and if these have the same diameter, we can spot that the centroid is right here, which means we're actually going to put this force right here, P, and we're going to add to it a moment equal to that force times the distance, which actually is not the distance from our origin, it's the distance from the bolt centroid. This is a very common student mistake, is to take the distance from here for the moment rather than this distance from the centroid of the pattern to the load. So let's see how that works. So here is our force. You'll see this is the exact same fastener pattern and load. This is equivalent to, we're going to take this force here, and we're now going to move it to the centroid. Now, this assumes we already found the centroid. Once again, we spotted this by inspection. So we're getting rid of that, and we're putting it here at the centroid. Once we have that at the centroid, we also are adding, we can't just move forces without paying someone off. We pay it off by calculating our M times E, and that tells us what our moment is. Now we have the equivalent force moment system at the centroid, and we're ready to start analyzing our fastener pattern. Now, if we look at the equivalent system, now what's going to happen is we have the axial force, which is going to cause a load per fastener, and we have the moment, which is going to cause a load per fastener. The actual equation is, first we're going to have P over A component, which is just our force over the total area. What is the total area? It's the summation of the areas of all of the bolts. So each bolt has a diameter. The area is going to be pi d over 2 squared. And if we sum all those up, then the stress, the shear stress in each fastener is just P over A. Okay? That's going to give us little stress components like this. Since the force was acting downward, those little components on each and every fastener is just this P over A stress. Okay? Now, we're talking about forces, but in order to calculate the force per fastener, we're going to have to go back to stresses, because it's the stiffness of these fasteners. So it's going to be the stress level on the fastener. And then once we know the stress level on the fastener, we can just multiply by the diameter of the fastener to get the force per fastener. So our stress components are P over A, and we have them equal and opposite, and they're in this direction here. And that is just for that 16 kilonewton force. Now we have stresses due to the moment. This is going to follow our same equation, mr over j, or mc over I. But in this case, the torsional resistance is J, which is the torsional resistance of the fastener pattern if you cut all of the fasteners through their shanks where they're attached, okay? And we're going to have that moment times the perpendicular distance from the centroid to each fastener divided by the J of the fastener pattern. That is going to be our stress per fastener. And it's going to be perpendicular, going back to statics, lecture 5 or whatever. We found out that R cross F equals moment. So R cross F equals moment. So actually, we're going to get a component that's perpendicular to the radial arm from the centroid to each fastener pattern center. The torsional constant is just the area of each fastener times the R. We're going to pretend that each fastener really has no moment of inertia about its own axis because that plate can just slide around that round fastener. So all that matters is what area it has and what radial position from the centroid. So if we take the A times the R, the distance from the centroid of the pattern to each fastener squared, that is the torsional resistance of that fastener about the center fastener pattern. We sum them all up, that gives us the total torsional resistance of the fastener pattern. So we're going to calculate the torsional resistance of the fastener pattern. We're going to calculate the stress MR over J. We're going to add that stress due to bending to any stress due to axial. But first, let's draw our stress components for moment. We already have the stress components due to the axial load. Let's look at the stress components due to the moment. Now, if our moment is acting like this, then each stress will be perpendicular. If you draw a line from the centroid of the fastener pattern, if you draw a line from the center of the fastener pattern to each fastener, we're going to get a component of MR over J. That stress is going to be perpendicular. Draw a line here, from here to the center of that pattern, and its component due to MR over J is going to be perpendicular. From the centroid to this one and perpendicular to that. All of these are perpendicular, right? Perpendicular, perpendicular. And then we draw a line from here to here, perpendicular, and it's going to be perpendicular. You'll notice, since this moment is going like this, all those components are aiming perpendicular to the radial line, but in the same orientation. See how that works? Okay, let's take a look at how that is then. We're going to see that in a moment. This is how we're going to actually calculate. If we take that J is the sum of the AR squareds, right? We said that. So that means we're going to have the sum of the A times, and the easiest way to calculate this is take the X position of each fastener minus the X bar of the fastener pattern squared plus the Y of the fastener, right? Because actually this little distance here, if we just focus on one of these, if we take this position, this distance here squared, plus this distance here squared, the square root of that is going to be this distance. So this X minus X bar from here is going to be X minus X bar, which is this dimension here. And this term here is Y minus Y bar, which is this little distance here. So that's giving us the little distance here, the little distance here. And if we square that, square this, that's this. And then if we take the square root, that's R. But then we square the square root since R is squared. So we just drop this. So it's just X minus X bar squared minus Y bar squared. We have that term square rooted and then squared. So this is our J. Got that? It's quite beautiful. Okay, now that we have J and we know R is just the distance of each, we are ready to show our little components. And once again, these are all perpendicular. Do you want to see that again? This is really cool. Got it? Okay. Now, You'll notice on each fastener, we have two components. And what students tend to do, since they tend to be reckless and careless, is just take those and either add them together, which is completely wrong, or take the root mean square of these together, which means 1 squared plus the other squared square root, which is also completely wrong. When can we take one component squared plus another component squared and take the square root to get the resultant? Anybody?
When it's on the origin?
No, when they're perpendicular. When they're perpendicular, right? Another point for you, Lex. When they're perpendicular, if the two components are perpendicular, we do that. So actually, this way of doing it is not ideal because we're going to end up, now we have to use the law of sines or the law of cosines, or we have to take little arrows and slide them over to make our parallelogram back like we did in statics. This is a hassle. There's an easier way to do that. So let me tell you the easiest way to do this. And I'm going to do that actually on the next slide. What we're going to do first is focus on our total stress is just P over A of each plus or minus the MR over J. But notice here, this is the little vector addition sign. We can't just add those together, take a root mean squared. We need to put them together using vector addition. And we're going to learn a better way to do this. A lot of books will cover this fairly well, but they will introduce this equation and they kind of leave it at that. And it's actually not the easiest way to do this. So stay with me and I will show you an easy way to do this so you can nail it every time. Okay? So once again, we have, this is our load. This is what we had. This is our equivalent force moment system. And now over here, we're going to put these stresses together appropriately. All right. So our section, so what we're going to do first is we're going to calculate our section properties. The way we do that is we're going to start by defining our X and Y coordinate system. We're going to use the lower left fastener as our origin, and we'll define our X to the right and our Y up. I encourage you guys to do this exactly the same way. That will give you the most success. Our X bar is simply the sum of the AXs over the sum of the A's, as always. The only difference is, instead of putting together little rectangles of properties, we're going to be putting together just little point areas from the fasteners, okay? Our Y bar is the same thing, the sum of the AXs, AYs over the sum of the A's. Our J we already defined was just each area. So what we're going to do is have each area times its X minus X bar squared plus its X minus Y bar squared. The stresses of the fasteners are put together with vector addition like this, but we ain't going to use this equation. This is not the easiest way to use this equation. Usually when I pitch this in person, I put 2 T's on there deliberately, but because to mess this up is to be the butt of bad work, okay? Let's take a look at how this puppy works. Here's what we're going to do. We're going to use these components. The easiest way to implement eccentric forces on fasteners is to calculate components of stress directly. We're going to take the shear stress in the X direction is any force that we find in the X direction over the total area plus, actually we're going to use minus, the M times Y minus Y bar over J of the fastener. This is just going to give us the X component. We're going to use a similar formula to get the Y component. Py over the sum of the area plus M times X minus X bar. Since this is an X and a Y coordinate system for our fastener pattern all lying in the XY system, our M is actually MZ, okay? X minus X bar over J. That gives us the Y component. You'll notice here we have an X and a Y component shown. Let me do that again. This first equation gives us the X component. And it looks like this. And you'll notice they're going different directions because we have both the axial load and the moment accounted for. But we're just getting the horizontal component of stress due to the moment. We're getting the horizontal component of stress due to the axial force, if there's one in the x direction, or minus x. And we have the axial, we have the x component of the stress due to the moment, just the x component. Now we take the vertical stress, it's just P, any y stress we have over A, and it's the moment and it's the y component of that moment, which is a function of just the x coordinates. That gives us two perpendicular components of stress. The beauty of this is, since we have two perpendicular components of stress, what that means is we now can use the root mean square to put these mothers together. And our resultant stress is just the x component squared plus the y component squared, square root of that whole enchilada. Got it? Now this is the stress, which we can use to evaluate the strength, or we can get the force in the fastener by simply multiplying the stress by the area of the fastener, okay? And these are our little resultants. Watch the little graphic as we replace each of these pairs of perpendicular stresses by their resultant stress. That's what we calculated when we're using these equations. This is the easy way to do shear analysis of fasteners, or the analysis of eccentric fastener patterns. Got it? All right. We basically learned what we need to learn, and now we're going to drive this mother home with a couple examples. Let's check that out. What did I say here? Blah, 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 blah. I already said that. Okay. This is a little example from Spot's text, machine design text, and our basic approach is like this. Now you can actually plug and chug in those equations I gave you, but the easiest way to implement accurate analysis is once again a tabular approach, where we're going to define our coordinate system and we're going to construct a table of properties. So let's start by defining our x and our y. We're choosing the lower left corner and we're choosing positive x to the right, positive y up. We then are going to start our table of properties. We're going to identify each fastener. So we'll have 1, 2, 3, 4, 5, however many fasteners we have. Now we could skip the diameter and just put the area, but I recommend you put in the first column your diameter of each fastener, okay? That will help you to keep track of what you're looking at. Now, if you have all the same diameter, it's not that critical, but if you have different diameters of fasteners, it is important that you can do this correctly. So stick in the diameter of each fastener. In this case, how many entries are we going to have in this table?
3.
6. You see we got 6 fasteners, 1 for each fastener. So one thing I didn't tell you here is what you also want to do first, once you identify your coordinate system, is identify these fasteners. 1, 2, 3, 4, 5, 6. We're going to have 6 fasteners. We're going to have 1, 2, 3, 4, 5, 6. Some down here. You got that? We'll put in the diameter of each. Then we'll put in the X position. Where is the first fastener? 0, 0. Second fastener. Looks like it's at 4, 0. Third fastener. 0, 6. Next fastener. 4, 6. Next fastener. 9, 0. No. 0, 9. Next fastener. 4, 9. You see how easy that is? That means yes. Next, we're going to put in the area. We calculate the area of each fastener. Bang, 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 bang. That's just pi d squared, right? pi d over 2 squared. That's our area of each fastener. You put it in this case, they're all the same diameter. They're all the same. They have different diameters, and some of these values will be different. And then we're back to normal properties. We're going to take the area times the x and the area times the y. And we're going to do that for each and every entry. We then can sum up the AXs and sum up the AYs. Our X bar is simply the sum of the AXs, this guy, over the sum of the A's, which is back here. Right? Bang, that tells us where this is. Now we can actually spot it by inspection in this case, but the Y we can't spot by inspection. The Y bar is equal to the sum of the AYs over the sum of the A's. We're going to calculate both of those before we continue on with our table. Got it? I'm going to erase this crap and we will continue. Now, okay, here's our CG calculation. We said that. And here's our CG calculation. We said that. Next, we continue our table to get our torsional constant. We can actually do that directly. What that means is this little term here means we're going to take the area of each fastener, which means we're going to take this, times the x position, which is this, minus x bar, which is that, square that puppy, plus the y position minus the y bar, square that puppy, add those two mothers together, multiply by that area of the fastener, and that gives you how much J this fastener contributes to the total pattern. Now, a really common student error is when they're calculating stresses, MR over J, they will take, if I ask them what's the stress in this fastener, they'll use the J for that fastener. This is the J of the whole pattern, not just of one fastener. Okay. So now we get an entry for each J. So in this case, how many J entries are we going to have? 6. We sum up all those mothers, and that gives us the J of the entire pattern. This is very, it's analogous, very similar to, near identical to everything that we've been doing for section properties with a slight tweak to be valid for fasteners. Okay, now, once we have the J of the pattern, we're ready to analyze our fastener pattern. We're going to use my equation that gives us the stress components. But first, we need to calculate our forces at the centroid of the fastener pattern. That means we're going to take that force and move it to the centroid of the fastener pattern, and we're going to add any moments that we find. You can use this equation if you define your loading where XL and YL are the location of the load, then you can just plug in. Now, once again, if this is our X and this is our Y and this is our force, then what is the X position of the force? In our coordinate system, our X position is just going to be 2, 4, 5, 6, 7. So that means we're going to have 7 minus XCG, which we found to be 2, times any Y force, which is negative 10K, right? And then we're going to have the Y position of the force. What is the Y position of this force? Actually, you'll notice this force is parallel to the Y, and therefore you can put in any value of Y, actually, like 0 or 1 or anything, and this will come out because you're going to have Y minus YCG times FX. This is not FX, this is FY, therefore this is 0, which means this whole term goes to 0. And there was no moment applied. Now, if there had been a moment applied, we would add that in. There is no moment applied, So this is 0, and all we end up with is this component, which defines as our MZ about the centroid. That's how we use that's how we can calculate our moment of this fastener pattern. You can just, if you follow my nomenclature for sign convention, you can just plug into this equation. You're going to have the full force at the centroid, and you're going to have the moment according to this equation. Once you have this, we're now ready to analyze our pattern further. We can actually implement this. Now, the way we're going to do this is with two components. We've got the X component. What is the force in the X direction on this fastener pattern?
Zero.
What's that?
0.
0. Another point. 0 force in the X direction. What is the moment? The moment is given by the equation we just said. It looks like it's going to be a negative moment. So now we plug into this equation, we get our X component of stress, and you can actually add that. So that means this is the P in the X over the total area. This is P in the X, which is 0, over the total area, which is right. Oh, I'm not showing you that. Let me show you that. Our area of this puppy, we should have up in here, we should have calculated our area as well. And that is just the sum of the AIs. And if you sum up these guys down here, that's where that's going to be, right? So this is 0 over this sum of the AIs. This is the moment from right down here. This is so now we're going to do, you can notice this equation gets implemented for each and every fastener. We have 1J for the fastener pattern, and we have 1 moment for the fastener pattern. We now, for each one, we're going to have for the first fastener, we're going to have a Y minus Y bar times our moment over J, and that's going to give us this component. The next one is going to be this term plus the moment over J times Y minus Y bar, bang, and so on. Then we have our second equation. Our second equation gives us the Y component of stress. You'll notice here that, once again, we have Py, which is actually negative in this case, divided by sum of the area. That's the sum of the area we have right here. And this is the total applied force. We have the moment, which is here, divided by the J, which is here, times the X minus X bar. That's the term that will change. So for the first fastener, it's X minus X bar. And next one, X minus X bar, and so on. We get a Y component for each one. Then we can take tau R, and we can put in this squared plus that squared. Squared of all that is our stress in the resultant direction. And then we can calculate our force in the fastener by taking our stress in the fastener multiplied by its area. Bing, 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 bing. And that's how we do it. So here's our tau R, and then our force per fastener. So tau R. So this is our component in the X, component in the X, component in the Y. This is the resultant of those two. This is on a per fastener basis. This is just area times stress. Bang. Now we know what the force is in each fastener. If we want to evaluate the shear, that's the shear force in the fastener. We just compare that to the allowable, and we can, so what we can actually put in also, we could put a margin of safety in this table if we wanted. For example, we could have the margin of safety for shear, right? That would just be, if we look up the shear allowable of a fastener, this margin of safety would just be the shear allowable of fastener divided by the shear minus 1 for each and every fastener. This is for shear. We could have the margin of safety for bearing. What we would do is take the same shear forces applicable, and now we've got that S against the bearing stress, or we could calculate the bearing stress, which is S over dt. That would be the FBRG of each fastener. It's just S over dt, and compare that to FBRU. If we have a S bearing of the fastener, then we can just write the margin of safety directly. If we need to calculate bolt bending, we can look and say, wait a minute, we look at the cross section of this plate, we can see we have this plate and it's bolted to something else. We would need to know what the thickness of each plate is. And now we'd calculate our eccentricity, right? And it's just that shear times the eccentricities of the moment. And we could calculate our bending of the bolt itself. FB equals that moment, which is SE times the radius of the bolt, or D over 2, over the eye of the bolt, as we saw in our little sub video on bolt bending. So we can actually do all that in this little analysis table. You guys understand all of that? Okay. So if we were to solve this using that kind of table, we would do it like this. We construct our table. You'll notice I have my forces in my Excel. This is not a great Excel, but basically we have our applied forces. Fx is 0, Fy is negative, Mz was 0, the applied Mz. We have the location of the load. I have the X position, and you can actually put in any My. Now, if we had a force, like if our force had gone like this, if we had two forces here like this, now we put in this Y position and this X position. But because our force is actually parallel to this and there's no X force, then we can simply put in any value for our Y position and it will work out. Okay, so these are applied forces. These are our location of the loads. I actually have some allowables here. We're not going to use SY. We're going to use SU, the ultimate, right? Once again, we have 6 fasteners. We have the diameter of each. You can ignore this. I use this as a way to, with some if statements, determine if some fasteners become ineffective. It allows me to analyze that quickly. So we have the X and Y position of each fastener in these columns. We calculate the area of each fastener, sum them all up. That's the area of everything. Multiply area times X bar, that gives us this. Area times Y bar gives us this. We do that for all the fasteners. Sum these up, sum these up. Sum of these over this is our X bar. Sum of these over this is our Y bar. Starting to look familiar? You don't actually need this column here, because we're not going to use that. We're going to be calculating our components. We can jump straight to our J, which means we're going to multiply. We're going to have the area times the X minus X bar squared plus the Y minus Y bar squared. And that gives us the J of that fastener about the centroid of the pattern. Do it again, 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 again. Sum those mothers up, and that gives us the total torsional resistance of the fastener pattern. We then plug into our little formula, P over A plus M X over Y, right, over I, or over J in this case. We get our X component and our Y component of stress. We calculate the resultant stress. We do the same thing for all of our other stuff. This is our stress in the fastener. It's off in some wacky direction. Now we can calculate the force in the fastener by just taking this stress and multiplying by its area. Take this stress and multiply it by its area to get the next force. These gives us the forces in the fasteners. You do not sum these up. These are all individual forces. If you want to calculate your margin of safety for shear, you could then compare this to the shear allowable of the fastener. As we said before, you could also have columns for bearing, bending, and other things. Got that? Here's another little example. This is going back to this example solved in a tabular manner. Once again, you'll notice here we have our applied loading. We have an XL and a YL of the loading itself. This is just showing my nomenclature and my load directions. We have 4 fasteners. We plug in the diameter of each. We plug in the X and the Y coordinates of each. Calculate the areas, calculate the AX, calculate the AY. Use those to get our X bar and our Y bar. Ignore that column. Then you take the area of each and you multiply it by x minus x bar squared plus y minus y bar squared. That gives you the J of that fastener about the centroid. Do it for every fastener. Sum them up. That's the J of the pattern. Calculate our x component of stress. Calculate our y component of stress. Calculate our resultant. Do that for all the rest of the fasteners. Our force in the fastener is just that resultant times its area. Do it for all the fasteners. And then we can analyze and have other columns for any margins of safety for any fastener. If I ask you what is the critical margin of safety for shear, you will have to calculate the margin of safety for each and every fastener and then report whichever is lowest. If I ask you what's the margin of safety for bearing, and if you have a bearing allowable for the fastener, you can just take the bearing allowable over S minus 1. If you don't have a bearing allowable, then you'll take this shear force and calculate the bearing stress, which is S over D diameter, T thickness. You'll have one value for each fastener, and you compare to the FBRU of the plates tying these together. FBRG, right? FBRU is the allowable bearing stress divided by FBRG, the bearing calculated stress, minus 1 will be the margin of safety for bearing. If I ask you for the bending stress to evaluate bending of the fasteners, you're going to look at what's our two plate thicknesses. Your eccentricity is 1/2 of the sum of the T's, right? T over 2 plus T over 2. That's your eccentricity. Each force, shear force, times that eccentricity is the moment in bending on that fastener, and the stress is MR over I of the fastener itself, of a round fastener of that diameter. That's how you analyze a fastener pattern. So that's how we analyze a fastener pattern when we have an eccentric loading. Enjoy.